where we're going to exemplify and look at how we actually work with the probability, the binomial probability distribution. I recap to you that now we play a little around with probability models. Probability models are extremely important in their own right for many different applications. It is also going to be important to us for doing statistics. But we're going to postpone the statistics of it just a couple of weeks now, while we get a little used to the probability reasoning and thinking here. So don't think that it has nothing to do with statistics. It has a lot to do with statistics. Actually, it has this to do with statistics that if I started sampling you, or I sampling a herd of cattle or a herd of people out there, and for instance, I wanted to register, are you sick or are you not? Are you left-handed or are you not? I would start throwing a coin and asking you, are you left-handed or not? And the answer would be right-handed, two options. That was a failure. Left-handed or not? Failure, 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 and then one success, success. This is a time causing where we extract data from real life. So we have the binomial system out there in the data extracting system. So this is why the binomial is extremely important for being intelligent about data analysis also. But let's learn it now, first of all. Now, small example from the little world out there where probability theory can help us in making decisions, also in real life situations. We have a call center in a phone company that are concerned with customer satisfaction. Actually, they are, I believe. It's essentially, especially important that whenever some error or fault are reported, then they're corrected within the same day. That's kind of a specification, a challenge the companies gave themselves. This is how we're going to deal with it. Now, assume that the probability of an error being corrected, one single error, they've learned maybe from previous data, that a single error will be corrected in 70% of the time, I should say, a single error is corrected within the same day, right? So their individual success rate is, you could say, only 70%. I mean, that's maybe a bit far off, but at least that's how the numbers are given to us. In 70% of individual cases, it will be handled, corrected within the same day. Then you could start throwing up different scenarios for the future, trying to learn from that and try to find out whether you want to change some things in your company. Now, imagine you are actually having 6 errors reported on a day. What is the probability that all of the errors are actually corrected within the same day? First step when we get these exercises is to try to turn it into math, turn it into formulas. That I think is often the big step. It's not rocket science, but it's still sometimes a challenging step to take the wordings of something real life thing and then turn it into some of the math and the frameworks and the formulas that I teach you to actually use, or you may even know some of the things from before. Here, let's introduce a random variable notation, x, which would be the number of errors corrected. And then sort of given the circumstances, given it's out of the 6 errors reported, right? Now, if we think about what we have learned, we could also express what we believe now. We would believe, I think we use this notation, that this random variable would be binomially distributed with p equal 0.0 and n given by 6. So that is the mathematical framework, model, expression of the system we've been put into here. Now we are asked a question. We are asked the question, what is the probability that all errors are corrected within the same day? Some probability related to x. The probability of x, what? That's the big step now. Can we express this probability exactly? Isn't that this probability that all errors are corrected. Isn't this the one? I would say. Well, that's an easy application of the binomial formula, because that would be 0.7 to the power of 6, right? We can find this number in various ways. Let me actually, before we find it, let me go on to the next question. I mean, I found it already, but before I actually compute the number, I'm going to collect the next question also. There could be another question. I mean, why would you be concerned with this question from a real-life perspective? Well, this is an important, for some obvious, for others not. This is an important point of probabilities. Probabilities reflect frequencies in real life, right? So if the probability is, say, of this event is like this, then it expresses how often will it happen in the future. And how often something happens in the future is important for your business management and how you do make money. If you have a feeling of how often certain scenarios will actually happen to you in the future, then you can maybe plan how many people you want to have in your office at these different times. Okay, what is the probability that at most one of the errors is corrected within the same day? At most one of the errors. Isn't that the same to say that, now I'm confusing, at most one of the errors is corrected means that x is either 0 or 1, right? So only 0 or 1 errors are corrected, not 2, 3, 4, 5, or 6. So it's a rather poor situation, but still, it's this is maybe the worst case situation. How often will that happen? Almost worst case, right? We are going to see if we can find this probability. Now, I think these are the two probabilities that we are going to try to find. This is the same to, this is also the distribution function taken in one. This is also f0 plus f1. There are different ways of finding this now. Let me show you the different ways. This one was a direct use of the binomial formula. It's also 0 out of 6 times 0.7 to the 6th times 1 minus 0.7 to the 0th, which is a 1. So it's just to say it's an explicit use of the formula. You can take your pocket calculator, our pocket calculator and go for 0.7 to the power of 6, right? 11.7% was the answer. Thank you. Yes? Now, it could also be found, actually. Look at this. There is a function in R which is called d-binom, for density binomial, right? So it has the small f function in R. You could simply evaluate that in the number in the number 0, in the number 6, then is the case. And then you have to put in the n, and you have to put in the p. These are options in this function. If I run this, luckily, I get the same number. Just to show you, this is the generic binomial density function, which is given by this d-binom function, right? You can plug in all n's and p's and x's there and get all answers. Quite convenient. There is now let me find the other probability, and then I get back to this one. Now, to get something like this, which is the probability that could involve many sort of density values. Of course, we could go and say d-binom 0 plus d-binom 1, and we could even find the formula and calculate it ourselves with our pocket calculator. And then we could add them together and see what the number would be. Is this really the one? Maybe I formulated myself oppositely than to what I thought I would have. At most, one of the errors is corrected. Yeah, this is what I formulated, right? Yeah, okay, we'll stick to that. Anyway. Luckily, there is also a p binom, which the p binom is the probability. So that is the accumulated, that's the capital F function in R. So we could evaluate that in 1. We could evaluate that in 1, and then I could just check to see whether this is not the same as d binom 0 plus d binom 1. Whoa, I was lucky again. So the probability of this worst case scenario is only around 1%. So only in 1 out of 100 days it would go as bad as this, right? This was 0.01 and then something more. This was another way of finding probabilities. I'm going to show you, for those who want to stay low-tech, that we can in fact use tables in the book for this. There are some tables basically showing, the tables in the book basically show, I'll zoom in a second. This is table 1 in the back of the book. It shows what is known as capital F of x of my slides. The binomial distribution function is given in these tables. So you can, and then you can see again before I zoom in, you have an n and you have an x, and then you have a lot of p's up here. So a lot of combination of n, p, and x to find probabilities. So if I zoom in a little bit, of course, I'd recommend to get used to using R. It's much more flexible. But it's just to show you can actually come across, in many cases, without using R. In our case, we would have to go find the relevant n. The relevant n for us was 6 in our example. What did we ask? We also need to, and hope, that we have the relevant p up here. If we don't have it, the table cannot help us. At least then you would have to interpolate somehow to use the table to get approximate values. Anyway, so the relevant distribution is given to us here. And if we look at the second one, we can see this is the one I just computed, 0.009, 0.0109. That was the distribution function taken in the number 1. 0.09. Actually, this could also be used if you were interested in, for instance, the probability of exactly 1, to ask another question, a third question you could say. Well, such a probability could be found by taking the probability of being below or equal 1 and subtracting the probability of being below or equal 0, which in this case is the same as being equal to 0, because you cannot be negative in this case, which means that we can subtract 2 subsequent capital F's from each other to achieve a small f. So if we subtract the accumulated probabilities from each other, then what is left is the individual, right? If we accumulate up to this and we accumulate up to the next, we subtract them, just the next one is left. So this could be used if you are going to try to find individual probabilities from the table. You could subtract 2 of those from each other and get the individual probabilities, rather than doing it yourself. But it's much easier in R, of course. So use R, that's a much more modern and relevant way of working with this for now, in the course, and for your whole future. Good. That's it for the example for the binomial. So let's skip it there, and now we make a nice break of 15 minutes.